the story on stars. We come back on the ground to discuss nuclear reactions, not fully in the lab, but partly. So just one note, the slides of yesterday's, including the notes, the things that I wrote, are available now on the website. So you can download them and have a look at them. So the goal of today's class is to first have a sort of a complement on quantum collision theory, and if time's allowed, to start the notion of the breakup of halonuclei. So yesterday, what we've seen is the different kind of reaction that can take place. So we've seen the notion of reaction. We've seen the notion of channel of reactions, which can be either open or closed. Looking just, so there are other conditions, but at the energy condition. So you have energy. You have reactions that are exoenergetic, so they will always be open. Some others are endoenergetic, so they require an incident kinetic energy threshold to take place. And so we've looked mostly at the elastic. Well, we've looked only on the elastic at the elastic scattering, and we've looked at the solutions of the Schrödinger equation, which have this asymptotic behavior, which are called the stationary scattering states. So you have the plane wave, which corresponds to the incoming plane wave, and then you have an outgoing spherical wave, which changes as the function of the angle, and this change is related to the scattering amplitude, and the cross section, the differential cross section for the elastic scattering is obtained as the square modulus of the scattering amplitude. And so we've seen a way to solve the Schrödinger equation doing a partial wave expansion. And when you write for each of the partial wave, you can write a solution of the radial equation as an incoming plane wave, which corresponds to what happens when the two particles come close to each other. So from infinity, and then they interact, and then they leave, they go back again as an outgoing spherical wave, and that wave is phase shifted from the initial wave due to the interaction, and you can compute a cross section from these phase shifts. And so what you need to do is to solve the Schrödinger equation in the short range part where the nuclear interaction takes place. So you solve that numerically, and then at a large distance beyond a certain radius, you know that you get this asymptotic version, and from there you can extract the phase shift. So that's how usually you do it numerically. We'll use a code during the exercise tomorrow to do that, so to solve the Schrödinger equation and then get the cross section. So what we'll do today, I will start because I was told that there were some questions about the notion of scattering length. So I will first briefly introduce that. Then I will see the notion of resonances, which I've not seen yesterday, and everything that I've said, as I said in the introduction, is true only for a potential that is short ranged, and of course that excludes Coulomb, which means that everything we've said is wrong. But actually, it's not. We can say that the Coulomb interaction complicates everything, but generally speaking, it's the same kind of solution that we will of way of solving the problem. And then we will see the notion of optical potential in a way to simulate phenomenologically the absorption from the elastic channel. So up to here, everything that comes in gets out. So all the particles interact, and then they're just elastically scattered. There is no inelastic scattering possible, no breakup included, no transfer, no fusion, no formation of compound nucleus. So everything is assumed to be only elastic, but there is a way to simulate that in using a complex potential, and that's the optical model, which we will discuss at the end of this complement on the quantum scattering theory. And then I will do a sort of an introduction to the breakup reaction. Hopefully I will be able to do an introduction on halonuclei. So you've seen this notion of halonuclei with Professor Meng. That was also discussed yesterday by David Krom. Here I would show you how these nuclei have been discovered, and they've been discovered through reactions. So that's why, and studied mostly through reactions. So that's why we need to describe reactions. So let's start with the notion of scattering length. So as I said yesterday, the function k to the power 2l plus 1, the times the cotangent of the phase shift is analytic in E. So that means in k square, where k is the wave number, and so it means that it can be expanded in powers of E or k square. And so in the S wave, if we look in the S wave, that function, so L here equals 0, just to make sure that we are talking about the same thing. So for L equals 0, then that function can be expanded, and the different terms bears different constant, and these constants have different names. So the first one is minus 1 over a, and this is what we call the scattering length. Okay, that's by definition what we call the scattering length. The second term defines a new constant Re, which is the effective range, and we call about the effective range expansion. When we talk about effective range expansion, that's what we mean. The term in K4 is the shape parameters, and then you have other terms. Okay, and so if you go back to what David discussed yesterday in halo effective field theory, basically one of the things that you can do is fit your interaction, your effective interaction between the two particles to reproduce these different terms. So if you know them from a more complex calculation, so no Course-Shell model calculation, or a many-body, a microscopic R matrix model, for example, then you can use these information and put them into your more simplistic model. For L larger than 0, then you have the same kind of expansion. We will still think of this as a scattering length, but for example, at L equals 3, this is a volume, it's not a length. And so we will keep talking, some people will keep talking about the scattering length in P wave or D waves, although it has not the dimension of a length. So it depends on this first factor. The cross section at low energy. So this is the formula that we've seen yesterday. At very low energy, the reaction is dominated by the S wave. So if you limit your term not to infinity, but you go just to the first term, then when you rewrite this, it's just 1 over k square, the square modulus of the sine of the phase shift. And if you are at low energy, then you can just use the first term of this expansion. So the expansion that we've seen here, you k small, so you can neglect these two terms. You're stuck with just the scattering length. So cotangent is 1 over tangent. So basically what you have is A is, so the tangent of the phase shift, which is for small values, it's equal to the sine. It's just A times K, minus A times K, sorry, and that means that the cross section goes to A at the power 2, where A is this scattering length. Okay, so there are two things to say. The first one is that at very low energy, the reaction will be isotropic. So the two particles come close to each other, they interact, and basically the outgoing wave, the scattering amplitude there is independent of the scattering angle. So that's the important part. It's because PL here equals 1. So for L equals 0, the Legendre polynomial is just 1. And so what you have is this. And when you integrate that over the angle, what you get is 4 pi A at the power 2. So A is really, as was mentioned yesterday by David in his talk, A is somehow a notion of how strongly the two particles will interact. So if A is large, either positive or negative, and we'll see in a moment what that means, but if A is large, it means that the particle will interact strongly. So if you remember, in his presentation, he gave a value of the scattering length for two neutrons, which is about, I will take a, okay, it's about 20, it's about minus 20 Fermi. So we are talking about particles which have the size, if you think of solid balls colliding, you have particles of the size of the Fermi, but the cross section is way larger, so it can be seen as a disk of a radius of 20 Fermi. So they really interact very strongly, even though they are small particles. So it means that the particles interact very strongly at low energy. That's the meaning of this scattering length. So it's the length at which somehow they scatter through their interaction. So just to have a kind of an idea of what's going on, what I suggest is to look at, imagine now that we have, so we'll make a very simple description. So let's assume that we have a potential, and I will take a square well potential. Okay, so with the depth V0, and so it's just a potential that goes up to R naught. And so what I will say is I will start with V0 nil, and then I will look at what happens to the phase shift as a function of the energy. So this would be delta 0, delta S. Sorry, that's the notation I've used, as a function of the energy. So if I have V0 equals to 0, that's what we've seen yesterday. It implies that the phase shift is nil, and that implies that the scattering length is nil. So your phase shift is nil everywhere. So the slope at 0, that's what it gives. That's the scattering length. It's the slope at 0. The slope at 0 is 0. And then what you do is you increase the depth of the potential. So what happens is if you look at when V0 decreases, what I mean by that is I take the interaction more and more attractive, exactly as what would happen between two neutrons, for example. Then what we've seen, the depth of the potential is negative. It means that the phase shift, it implies that the phase shift will increase and become positive. So what you will have is something like this. So what happens here, I don't remember. I don't know exactly. The only thing I know is that at infinity, it has to go to 0 everywhere. And so the important thing here is that, going back to what it means, is that the slope here is given by minus a. Okay, that's what it means. That's the scattering length. And so if I plot here, that's my scattering length. I will put my 0 over here. When V0 is 0, the scattering length is nil. Okay, nothing happens. And when you increase V0, when it starts to become negative, then what happens is that you move in that direction. Okay, so it means that the potential becomes more and more attractive. And what happens is the slope here will tend. This slope will tend to move higher and higher in that direction. So you will have a slope that goes more and more higher and steeper and steeper, and your potential will move. The phase shift will become more and more start to grow more and more, because the potential becomes more and more attractive. And then you will move, eventually reaching a very negative value, so minus infinity, and then something happens. And what happens is that at that value, your potential is so deep that it starts to bind the two particles. So what happens is, if you continue to have that, the potential will start to bind the particle. And if you, so there you have A that you have A that that decrease, meaning that it's initially negative. And then a miracle happens. So you have V0 decreases to the point that you have a bound state. And when you have a bound state, Levinson theorem kicks in, and so it means that the phase shift should start from pi, but you still have to reach 0 at infinity. So let's assume that pi is here. Then what will happen is that your phase shift will decrease. Maybe something happens here, but in the end, it always goes to 0. And once again, the slope here is given by minus a. Since the slope now is negative, it means that so here you have a bound state at e equals 0, and what happens is that you move to plus infinity when you keep lowering the potential. So here V0 is much lower than 0. It doesn't make any sense what I wrote, okay? Lower than 0 is lower than 0. What I mean here is that there is at least there is one bound state, okay? And so you get an A which is now plus infinity, and if you keep lowering, what happens is that this slope here starts now to move in that direction. So you will have something that is less and less steep. So at very zero energy, you will have at very small energy, you will have a slope that is strongly very steep, and then move up, back up, and then it will come down in that direction, eventually reaching 0, which means that you will have a slope which is horizontal at the beginning, and then A will become negative again, and then the potential will now rise in this direction, and then eventually decay until you reach minus infinity, where the potential is so deep that you have two bound states. It means that you will start from 2 pi, which is somewhere here, and once again you will go down. So you can really, it's just a game. You move up and up, up and down here around that axis. The fact that you have two neutrons, the A for the two neutrons is over here. So it's minus 18, minus 19 Fermi. So it's very negative. We are measuring everything in Fermi. The size of the neutron is about 1 Fermi. So minus 18 is something very big. So if the interaction between the two neutrons were slightly higher, then we would have a bound di neutron. And that's what relay. And so what David told us yesterday is that for he looked at carbon 22. So he looked at the carbon 21 neutron interaction in carbon 21. That's right. Yeah. Okay. So carbon 21 neutron, and what he said is that the scattering length for carbon 20 neutron is much lower. It's around 2 Fermi. Was that, or I don't remember. Yeah, okay. So it's much lower. So this is the reason why he can, in his model, say it's okay. I look at the leading term. What is very important is the neutron-neutron binding. It's not the neutron core. The neutron core, yeah, it's there. You need it, but you can neglect it at the first order because the scattering length is very small. Okay. So does that answer your questions, or this? Not sure it's clear, but yeah. Yeah. No, no. So you can have, and actually, so with the scattering length, you cannot say anything on the number of bound states. It's no. So you because if you are positive, you could say there is at least one bound state. Okay, but it's wrong. Because what happened is that if you take V0 positive, so you have a repulsive interaction, then the scattering length will become positive. So it will move in this way. So if you go with V0, so if you move in this direction, so here you will have V0, which is positive, then what happens is that the scattering length will become positive. And so, yeah. So it means that you cannot even say that. It could be strongly repulsive. Okay. Yeah. Yeah, exactly. Yeah. If you know the interaction is attractive, then so if you know the sign of the phase shift, basically, um, then you can say something. Okay, so this was a small parenthesis on the idea. So what I want to discuss here very quickly is this notion of resonance. And so a resonance is, in general, just a large variation of a cross section over a short energy range. And so here I took an example. I liked the example. It's a reaction of carbon-13 plus a nutrient that forms a nitrogen-14 plus a gamma. It's a reaction that takes place. It takes place during the CNO cycle. So it is very important for nuclear astrophysics, and so you need to know that cross section rather reliably if you want to simulate stars where the CNO cycle is important. And so here what is plotted. So the paper, I took it from a paper from Dubovichenko from the physics of atomic nuclei. This is actually a translation into English of a Russian journal. During the Cold War, the Americans wanted to know exactly what the Russians were doing, but not all the physicists were fluent in Russian. So what they would do is basically translate the journal. So people would translate the journal into English, and they kept doing that. So when I contacted Dubovichenko to get the figures of his paper, I wanted to have the proper figures. He sent me the figures, but the problem is that he published them in Russian, so it's in Cyrillic. So you have KV here, and here you have the S factor. S factor is a measure of the cross section. It's not the cross section exactly, and so it's in KV bonds. That's why you have these weird symbols here. And so what you see here is that at an energy of the proton that changes over a few hundred keV, you have a huge variation in the cross section, about 2 orders of magnitude. So it's a huge change. And so the question, of course, this is radiative capture, so it's more complicated. But if you look at the elastic scattering, the total elastic scattering, what we have is 4 pi divided by k squared, sum over L, 2L plus 1 sine square delta L. That's what we've seen. So if delta L is close to n pi, the contribution to the cross section is small. It's close to 0. Okay, it will not be very significant. Now imagine that instead of that, the phase shift goes through pi half. So if, on the other hand, the phase shift goes to 2n plus 1 by half, then the contribution is maximal. So you have a huge contribution, or a huge change. And if you go from somewhere like 0 through pi half and going to pi very quickly, your reaction will your contribution to the scattering will be very significant. And so here it's slightly more complex, but it's exactly what happens. And what is interesting is that so this is exactly what happens. So here you have the phase shift in degree as a function of the energy in keV in the 3s1 channel for the proton on carbon-13. So the points are experimental data, and the solid line is the potential model of Dubovichenko. And here is his potential model used to compute the cross section. And so what is interesting is that it is so it's related to one and only one value of L, and so to be complete in one partial wave. So it has the same kind of quantum numbers as a bound state. So you can see that as a bound state in the continuum. So it's not bound, but it's just a resonance. Very hand waving, you see the two particles come close to each other, and there they interact for a while before being separated. So if you see the particles scattering very quickly, they will not interact very strongly. The phase shift will not be very large, be away from pi half. But if they stick together for a while before being scattered, then you are at the resonance. That's where the particle stays there. Okay, so that explains this kind of behavior. And that's the notion of resonance. And you can see them, for example, that's a case we'll see later, either today or tomorrow, for the breakup of beryllium-11. Here is the breakup cross-section as function of the relative energy. It's an experiment performed by Fukuda and collaborators at RIKEN, and it's a reaction for beryllium-11 impinging on carbon-12. So it's a nuclear-dominated reaction where the beryllium-11 breaks up into beryllium-10 and a neutron. We'll see that in detail. And what you see is that the cross-section exhibits two peaks here at low energy, one here and one here, and they are related close to resonances, states in the spectrum of beryllium-11 that are well known and that can be described as one of these resonance states, so as a beryllium-10 neutron resonance, and so they influence these breakup reactions. So we'll see that tomorrow and certainly Friday. So what about the charge case? So we've seen everything we've seen. Well, but for the resonance state, it was proton carbon 13. So the problem is, up to now, what we've always said is that the potential is short range. It's nuclear interaction. We've said, well, I said, we do nuclear physics, so that the interaction is short range. So we just need to look at what happens at short distances. But that excludes the Coulomb, and unfortunately, well, it's good for us, so we exist, and something happens, and you can have chemical bindings, and but for the calculation, everything is more complicated, as we'll see in a minute. So you have a Coulomb interaction that puts everything, and that interaction does not satisfy these properties. So you have to do something about that. So we define usually this, what we call the Sommerfeld parameter, which is basically the product of the two masses, ZA, ZB, E squared over 4 pi epsilon naught, depends on the Coulomb gauge that you use, divided by H bar V, where V is the relative velocity between the two particles. And so introducing this, you can write the Schrödinger equation in the presence of a Coulomb interaction as this. So just to make sure that we agree on everything, so you look at 2 eta K divided by R. So I replace the Sommerfeld parameter by its value. So that's twice ZA, ZB, E squared over 4 pi epsilon naught. You have a K over here, and it's R. So you already have something that looks like, H bar V times R. And so it already looks like a little bit like the Coulomb interaction. So I just remind you the relative velocity, it's H bar K over mu, which is the reduced mass. And so what we have is, if we replace V by its value, we have twice mu over H bar square, ZA, ZB, E square over 4 pi epsilon naught R. And so that's basically twice the reduced mass divided by H bar square, ZA, the Coulomb interaction. Okay, so that's exactly what you want to have here. We have divided everything by H bar over 2 mu to get the to get that equation. So this actually can be solved exactly. So there were very smart people who at one point could solve that equation without Mathematica. And so they got the solution has this behavior, and it looks very much like what we've seen for the stationary scattering states. So you have a plane wave here, you have an outgoing spherical wave here. The only difference is that you have this eta ln kr that appears here in the incoming wave and here in the outgoing wave. So what you add is a smoothly varying, slowly varying phase to the problem, and in each time you have this eta which contains all the information about the Coulomb interaction. And so what it means is that it's exactly the same case, but you add this slowly varying phase. And why you have this slowly varying phase is because Coulomb is first slowly varying and it's long range. So you need to take that into account up to very large distances in this asymptotic description, asymptotic part of the solution. And so you can compute this scattering amplitude, which is the Coulomb scattering amplitude, and the Coulomb scattering amplitude has this rather horrible form. So once again, it depends on eta, which is this the strength of the Coulomb force divided by the sine square of theta divided by 2, and then you also have a phase here with a Coulomb phase shift, which is the argument of the gamma function extended to the complex plane. So I won't go into the detail. It just adds to the phase shift to the to the phase shift between the incoming and the outgoing wave. And so this is the Coulomb scattering amplitude, and you can do exactly the same kind of game as what we've done before with Ji and Js to try to get the cross section. And it's actually exactly the same game, because the only difference that we have from the previous case is this very slowly varying phase. And so when you derive it with regard to R, you will add a term which goes as 1 over R. And so it basically, you can neglect that compared to the dominant part, which is either the spherical outgoing wave or the incoming plane wave. So it's exactly the same kind of discussion. And you get the cross section in exactly the same way by taking the square modulus of the Coulomb amplitude, and you get what we call the Rutherford cross-section. And so the Rutherford cross-section is called Rutherford because Rutherford not only was an excellent experiment, one of the best experimental physicists, one of the best physicists who ever lived, and so he was mostly known for his experimental work, but he derived that cross-section to try to explain the experiment by Geiger and Marsden, his two postdocs or PhD students, I don't remember. And so where they did the experiment with the alpha scattering on the gold foil, and where they also looked not only at forward angle, but also at backwards angles. And that's where they noticed that a nuclei where alpha particles were back scattered. And so that's where Rutherford has the idea that you need to have a nucleus in the atom was not the vision of Thomson, which is the plum pudding, but it has to be a nearly point-like nucleus with an atomic cloud. And to explain that with point-like charges, he got that cross section. So he was not only and this was before, of course, the experiment was 1910, 1911, but that was an experiment, and so it was before the invention of quantum mechanics. So if you solve that in classical mechanics, you get that value, but if you solve it in quantum mechanics, you also get the same. So he was lucky, you could say, but he was smart cookie. So so what is interesting is to note the divergence at theta equals 0. So you divide by the sign of 0. So you have that divergence brings lots of difficulties when you try to solve these problems. Yeah, so now we know how to solve for the Coulomb interaction. What happens when you have a nuclear interaction in addition to the Coulomb part? Well, you do exactly the same stuff, okay? What you'd say is you start from the Coulomb wave function, so it's at least it's asymptotic shape, which is this one. So an incoming plane wave and an outgoing distorted wave, both are distorted by the Coulomb interaction. Coulomb interaction is infinitely ranged, so you need to take that into account in your calculation, sorry. And so what you do is basically do exactly the same thing, and you add a term with an additional scattering amplitude, which is due to this short range. For us, it's the nuclear interaction, but also times an outgoing spherical wave distorted by the Coulomb interaction at long range. Okay, so you have this epsilon 2kr, which comes back again and again in your derivation. And you can get the cross-section, So the total scattering amplitude now is the sum of the Coulomb amplitude plus the additional amplitude, and the total cross-section is the square modulus of the sum of these two amplitudes. These two amplitudes are complex numbers, so there will be interferences between the terms. So you need to take that into account. It's the square modulus of the sum of two complex numbers, and so you will have interference between them. So it's not, you can't just say, okay, you have the Coulomb on one part, so the cross-section is the sum of a Coulomb cross-section and a nuclear cross-section. That's not the case. It's the sum of two amplitude, and they will interfere, and that will give you weird shapes, and we'll see that in a moment. Because of the divergence that I've mentioned, at very small angle, the Coulomb amplitude is always much, much larger than the additional amplitude. And so the cross-section at very forward angle is always very close to Rutherford. That's usually how people who experimentalists do to normalize their beam when they perform reaction, is you look at very forward angle and you know you should be Rutherford. And so you can normalize your beam and the beam intensity, this Fi that I've mentioned yesterday. So you can measure that. If you know properly what's inside the target, then you can normalize your beam just by saying the cross section should be Rutherford at very forward angle. So that's one way of doing it. And so usually what you plot is the ratio of the cross section to Rutherford, because otherwise you vary over orders of magnitude. When you plot the ratio, everything looks nicer, and that's exactly what these people have done. This is an analysis of helium-6 scattering. So helium-6 is a 2-neutron halo nucleus, so it's equivalent to the carbon-22 shown yesterday. We'll discuss that a bit later at the end, hopefully, of today. And so it's impinging on zinc 64 at low energy. I think it's an experiment performed at probably Isolde. So at CERN, and here is the calculation of Manoli Rodriguez Gallardo from Sevilla, using a 4-body description of the reaction, 3-body description of helium-6, and a 1-body description of zinc. And so what you see here is the elastic scattering. So the data are the points, okay, and the calculation, the very complicated, difficult, and challenging calculation of Manoli are shown by the solid line here, which agree very well with the data, showing that she knows what she's doing. But you see the ratio. What I wanted to illustrate here is the ratio to Rutherford. So you go to 1 at very forward angle, and then you see that you should see here you have small oscillation. That's the interference I was mentioning, because you sum two amplitudes, two complex amplitudes. And then you have a huge drop, which is usually called as a Coulomb rainbow, and that's where the nuclear interaction becomes dominant over the Coulomb interaction and absorbs part of the it absorbs part of the flux, of the elastic scattering flux. So we'll see that later today in the optical model. This is actually similar. If you have done a little bit of wave optics, this looks like these airy function that you get in Fraunhofer scattering, diffusion for, you have a plane wave impinging on half a screen, so just half of the space is black and the other is free for the light, and you look at the screen at the large distance, you should see if the light is coherent, you should see this kind of of change in the magnitude of the line due to the screening. So it's a bit similar. You can also do a partial wave analysis. So if you write the wave function partial wave for partial wave, you have to solve that equation, usual term, kinetic energy, the centrifugal term, the Coulomb interaction, and then you add this short distance nuclear interaction. At large distance, this term becomes negligible. So, and once again, smart people solve the problem in the past, and you get actually what we call, it's a, once again, second order differential equation. You have two independent solution, which is the regular and irregular Coulomb functions. Okay, here, these two, FL and JL, and they behave exactly as what we should expect, as a sine and a cosine, with a large, with once again this phase, this slowly evolving phase that represents the Coulomb interaction, and you have a phase shift, which is due to the Coulomb phase shift, which is given by the argument of the gamma function, depending extended to the complex plane and depending on the Sommerfeld parameter. And so you do the same trick. You can define A and B as an amplitude CL times the cosine or the sine of the phase shift, and so you get this wave function, and you can derive the additional scattering amplitude in this way. So it's exactly similar to the previous one. The only difference is that you have a Coulomb phase here. So even in the additional phase, in the additional scattering amplitude, you have a Coulomb plays a role. So you can't, you can't say the additional is just due to the nuclear interaction. The Coulomb interaction is there. You have a Coulomb phase here that plays a role. So that shows that Coulomb is more complex than just saying, okay, there is one part of the cross section which is due to Coulomb and the other due to the nuclear part. And so you can also have the same kind of interpretation in terms of a scattering matrix. So instead of looking at the sign, you can look at the ingoing and outgoing Coulomb function, which is obtained as a linear combination of the, it's equivalent to the Hankel function when you look at the Bessel function. It's also a linear combination of the two regular and irregular Coulomb functions. And what you get is it's an outgoing, incoming spherical wave distorted by the Coulomb interaction once more, or an outgoing wave. And what you have is this: you have an incoming wave and an outgoing wave, and the outgoing wave is phase shifted by the interaction due to the short range interaction. So you have this incoming wave distorted by Coulomb. Okay, they come close to each other, then you interact. It delays or hasten the scattering of the two particles, and then they are phase shifted and in the outgoing wave. So it's exactly what we've seen, but everything is more complicated. So it's just that. Questions? Yeah. Coming back function from far away should be bandwidth. I don't know why. No, because you can't switch off. Well, it would be nice if we could say to the particle, switch off Coulomb when you come close to each other, and then it's just in the outgoing channel. So they come close to each other, they feel Coulomb. So at very, very large distances, so at infinity, you can say, okay, the Coulomb is not there, okay? But when they come close to each other, way before they start interacting through the nuclear interaction, they repel each other. And so the incoming wave is sensitive to the Coulomb, so it slows down the two particles that come close to each other. Do you see that? And once they have interacted, they go away, they have stopped interacting through the nuclear interaction, but they are still repelled from each other due to the Coulomb interaction. So you need to take that into account in your calculation. Yeah. Yeah, exactly. So, and that's why you have this term is never, it's a logarithmic function. So it never stops appearing, but it gets, the further away you go, the less important it becomes. And so that's why you have this kind of logarithm in the expression. It's because of the 1/r behavior of the Coulomb interaction. Okay? Yeah. Say that again. Yeah, it will appear in this additional scattering in this additional phase shift. So the in your in and it will be, I don't know if I have an expression here. Yeah. So it's more complicated because you have to take the square modulus of everything. But once again, if your phase shift goes through, so the additional phase shift goes through pi half, then you will also have a resonance. Okay. Good. So good. So we'll now move to this notion of optical model. And so the question is, so far we've only described elastic scattering. So everything that comes in gets out of the reaction. So nothing stays there. So the particle come in and they are elastically scattered. In real life, so what the people actually measure, of course, you have other open channel. You can have breakup, you can have transfer, you can have inelastic scattering, and that has to be taken into account when you want to reproduce that by a simple model. So this is a kind of, so you can include them explicitly, and that's what we're going to do with the breakup part. But it's rather difficult. So here is one example for the transfer. So you have a transfer reaction, and you can also do the same kind of discussion, but this is more complicated because the two channels have to be included in the model of the reaction. So you need to have a couple channel calculation of the reaction. So you have an incoming channel, which can also be the outgoing channel. They also can be elastically scattered, but they're coupled to the transfer reaction where some nuclei from one nucleon, some nucleons from one nucleus are transferred to the other nucleus. So it means that everything can be rearranged, and you have changes. So you can do the same thing. There are two notions I would like to introduce before arriving to the model. The first is what we call to be the reaction cross section. It's actually something that experimentalists can measure, and it's the sum of the cross section for all the channels but the elastic scattering. Okay, so when you exclude the elastic scattering, you do the cross, and that's the reaction. So that's when the particle interacts inelastically. That's what it means. There is another notion that will be very important for the notion of halonuclei. We'll see in a minute. And it's the notion of interaction cross-section. And that's where you exclude from all the channel the elastic and all the inelastic channels. So when B is excited, when A is excited, and when both A and B are excited. So you remove these channels. This is easier to measure because it means that the outgoing particle have to change. So if you put beryllium-11 in, something different from beryllium-11 has to come out. So it's easier to measure because you just analyze. You have a sweeping magnet, for example, and from there you can analyze the mass to charge ratio. If it's no longer beryllium-11, it means that it's something else, and you can count them for that reaction. So it's easier, and we'll see that's how Tanihata actually discovered these halonuclei in the mid-80s. And so the problem is, how do we account for that on a phenomenological way in the model that I've seen? So not getting something too complicated, getting something a little bit more simple than doing this difficult, complex potential. Complex or difficult. Complex is yeah. should be careful when we use complex, but a difficult coupled channel calculation. But we use complex potential, which are easy, but complex. So the idea is you, instead of a real potential, you add an imaginary part. And when you do that, you solve the Schrödinger equation exactly in the same way. But then what will happen is that we will see that you can absorb part of the elastic flux. And how do you measure that? Well, you compute the divergence of the of the quantum flux, so the divergence of J. So what you need to do is, what we are going to do is compute the divergence of J and hope that it's no longer a nil. So try to see something that is different from zero. So what you need to do is to compute the divergence of 1 over mu, the real part of psi star minus I h bar gradient psi. Okay. So I will rewrite this in another way. So mu is a reduced mass, so it's not it does not vary with the position. So you have the gradient of psi complex conjugate minus I h bar gradient psi plus psi I h bar gradient psi star. Okay. And I divided by 2. So I sum the complex conjugate of the two I sum the function that I want to compute real with its complex conjugate. And so what I get from here is one. Yeah, I can get h bar out. I can get I h bar. Minus I h bar divided by 2 mu. And what I have here is gradient of psi star, gradient of psi plus psi star, Laplacian of psi, minus, I have a minus sign because I took minus I out of here, and here I just have I. So that's why I have a minus. And I have gradient of psi, gradient of psi star, minus psi, Laplacian of psi star. So what I can see is that these two terms will cancel each other. And so if the potential were real, of course, these two would also cancel. But the potential is not real. The potential is complex. So it has an imaginary part here. And so if we take here, so this term, I can evaluate it using that Schrödinger equation. And so what I get is that this is minus I h bar divided by twice the reduced mass. Psi star. What I have here is 2 mu over h bar square. Yeah. So no, yes. So I have u opt minus e minus. Oh, sorry. Star. Oh, no. That's not. That's it. Yeah. Minus here exactly the same thing, but the complex conjugate. So psi 2 mu over h bar square times u opt, but complex conjugate because what I have here is psi star. So when I write that, I take the complex conjugate of that equation minus e psi star. So not very clean. So these two terms cancel each other. The real part of the potential vanishes, and so the only thing that remains is the imaginary part of the potential. So what I get here is, so 2 mu, yeah, I can also 2 mu goes down, h bar and h bar simplify, and so what I have is twice over h bar, the imaginary part of the potential, times the square modulus of the wave function. Question: what should be the sign of this divergence of the flux? Yeah. So you need y. Yeah. 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 Exactly. So you have something coming in, but you know that part of the flux goes away. Okay. So you need to absorb the flux, and so this has to be negative. 2 is positive, h bar is positive, the square modulus of a complex function is positive. So that means that W of r has to be, of course, negative for all value of r. Okay. So that means that the imaginary part has to be negative. If you have a positive part of the imaginary part of the imaginary term, it means that you will have a source term in your equation. So something comes into your elastic channel without any so you would have a source term in your equation, and that doesn't make much sense. Okay. The fact that you have an imaginary, a complex potential leads to a complex phase shift. Okay, so you have a real part and an imaginary part. The fact that you have potential has to be negative means that the imaginary part will be positive. It's the same thing as what we've seen, but now in the complex part. And if we look now at the S matrix, so I just remind you that the S matrix is E at the power twice I delta L. So this is exactly the same thing. You can do the same kind of analysis, but what happens now is that you have, if you separate the real and the imaginary part, you have the real part that stays a complex phase of modulus 1, but then you have this term here, this factor here, which is E at the power minus 2, the imaginary part of the phase shift. Since the phase shift is positive, this is negative. And that means that if we look back at the partial wave expansion and the behavior of the solution of the radial Schrödinger equation, you have an incoming wave, okay, of modulus 1. Well, there is a normalization here, this 1 over 2 pi at the power 3 3/2, but you have something with basically here a model 1 and something here with a model that is less than 1. So you really have an absorption from the incoming wave. So here less comes out as come in, and that makes sense. Okay, you have particle coming in and then they change. What happens is you have all other open channel, and so that absorb part of the flux of the probability flux, and so that means that you have an amplitude in the outgoing wave which is smaller than 1. Yeah, So you wonder maybe why we talk about the optical model. It's actually very similar to what they do in optics. So if you solve uh, the Maxwell equations, for example, for particles, for photons in a fiber, in an optical fiber have an absorptive part. Part of the photons, not all the photons go through, some of them are absorbed, and you simulate that by adding a complex refraction index of the material of the fiber or the medium where the light through which the light goes, and so that simulates the absorption using an imaginary part of the complex, an imaginary part of the refraction index. And something that the opticians have done for lots of time. And so, well, that's where the name comes from. So what is the absorption cross section? So let's assume you have a potential and you want to compute the absorption cross section. So the quantity of the cross section that is absorbed by this imaginary part of the potential. So I will do exactly the same thing as what we've done before, but in this case for that interaction. So my absorption cross section is the integration of the divergence of this of the flux, of the probability flux over the entire space, divided by j divided by ji. Once again, I take the number of particle in the target to be 1. Because this is negative, I have to put a minus sign over here. Okay, and so this means that it will be proportional to. We've just seen where here. So this divergence here is proportional to that expression. So we can say that this will be proportional to W of R square modulus of psi R integrated over the whole space. So to compute this, I go back to the expression. To compute this, what I will use is to use a Gauss theorem. So I will keep the minus sign, and instead of integrating over the whole space, because I have to integrate the divergence, I will integrate over the sphere, which goes of radius r, that goes to infinity, and I will integrate now just the flux of the probability flux over the surface of the space of the sphere. So once again divided by ji, and this is minus integration over a sphere of radius r going to plus infinity of j on r square d omega. So my wave function, I know that my wave function, because I have to integrate that over infinite at the sphere at very large distance, I can take back the behavior of the wave function at infinity, and I find once again 1 over 2 pi at the power 3/2 I divided by 2kr sum over L, I at the power L, square root of 4 pi 2L plus 1 times the incoming wave. So I do not take into account the Coulomb. I just look at, for a short range interaction, I neglect the Coulomb times minus SL, and the outgoing wave IKR minus L pi half okay, times the spherical times the spherical harmonics. So what I need to do is to compute J, which is once again 1 over mu, the real part of psi star minus A H bar minus I H bar psi. So, yeah. So what I get is, what I want to get is only for r going to infinity. So I will do exactly the same thing, that I will take the derivation only on r and only on of the exponential. And so what I get is 1 over 2 pi at the cube, 1 over mu. It's 1 over 4 k square r square, the real part of sum over L prime minus I at the power L prime, square root of 4 pi to L prime plus 1. So that's the incoming wave, but complex conjugates minus L SL. Complex conjugates R minus L pi half. Should be primed everywhere of omega. That looks okay. And the only thing that happens, so I have my minus I H bar. The only thing that happens by the derivative is that you multiply by a ik, and you have exactly the same thing, sum over L, I at the power L, square root of 4 pi to L plus 1. And now I have a real ingoing wave minus L pi half minus SL R minus L pi half. And do I have everything? Looks like it. And sorry. And this goes in the outgoing radial direction. So what you need to do is to do the integration over over the angle. So you take J, you project it over 1r, multiply by r squared, and integrate over 4 pi steradian. Maybe I will skip all the details and get to the results. And you obtain in the end, after derivation, minus 1 over 8 pi square h bar k over mu 1 over k square sum over L 2L plus 1. So taking into account, you will have the product of these two spherical harmonics. You integrate over the angle, and so you cancel. You have only one sum over L, and you have 1 minus eta L square. So knowing that Ji is 2 pi at the power minus 3 times v, which is the relative velocity, what you get in the end is an absorption cross-section, which is pi divided by k square sum over L, 2L plus 1, 1 minus eta L square. And so this is the final solution. So what you see is that if you have an imaginary part which is 0, so you have a real potential, eta L equals 1, and therefore there is no absorption. So the absorption shows the strength that you have. So if your imaginary potential is very large, eta will be rather close to 0. You will have a strong absorption, and what happens is that the absorption cross section will be large. Now, what can we do with this? We can look at induced fission. This is the fission cross-section for uranium-235. You have uranium-238 here. And what you see is that there is the whole region of resonance. But let's have a look at what's going on here at low energy. Okay, so you have a neutron, an incident neutron of less than an EV energy. So it's really thermal neutrons. And I have two questions for you. So I've worked so far, so now it's your turn. The first one is, knowing that this is a can you see something? So knowing that this is a double log, so this is the log of the energy in electron volt, this is the log of the cross-section in bar. The first question is, what is this behavior? And the second one is, using this formula, can we easily understand it? Can we easily explain that behavior? So okay, so that's the expression of the absorption cross section. First question is, what is this behavior, and can we understand it like this? So assuming that but for the elastic channel, the only channel that is actually opened here is the neutron-induced fission. So it means that when the neutron arrives on uranium-235, it either elastically scatters or it is absorbed. And so you can relate this neutron-induced fission cross-section to the absorption cross-section. So the question is, first, identify that behavior. It's a straight line in the double log plot, so that should be not too difficult. And the question is, can we understand that in a simple way? So on the first question, we can guess, okay? You have nothing to lose but your pride. Sorry? Yeah, so what is the energy behavior of that curve? That's the question. Hmm? Yeah, it's Yeah, but it's minus a half actually, so it's partly okay. So because you change, if you look at that, the analysis is good. So you here, if you look over, if you look at this is 2 orders of magnitude in energy, okay, and you decrease by 1 order of magnitude in the cross section, okay. So it means that the answer here is that your nutrient-induced fission cross-section behaves as, at low energy, behaves as 1 over K. Okay. Now the question is, can we understand that in a simple way? So what should I do? Excellent. Very good idea. Okay, so I don't want to lose this. So first point, low energy. So on the L equals 0. So what I can say is that the absorption cross section is pi over K square, 1 minus eta 0 square. Okay, that's the first thing. Eta 0 square is actually the square modulus of E at the power 2I delta L, where delta L now is complex. Okay. So what I can say is that this phase shift to a multiple value of pi, but I don't care of that, is very close to 0. It's low energy, so I know that the phase shift should be small. So what I can do is say, well, this is about this is about the square modulus of 1 plus 2I delta L. Okay, it's just an approximation. I do a first order approximation. And so this is about 1 minus 2I delta L complex conjugate times 1 plus 2I delta L. Okay, and I neglect the higher order terms. So when I do that, 1 times 1 is 1, and then I have 2 times I, and I have delta L minus delta L star, and I drop all the other terms. The higher order terms is also order 2, so I can neglect that. So this will, in the end, give you something which is about 1 minus 4 times the imaginary part of the phase shift. And so 1 minus eta 0 square is about 4 times the imaginary part of the phase shift. Now we are at low energy, so the phase shift behaves as well, I kept the L, but it's 0. So and 0, and when K goes to 0, this phase shift will behave as we've seen. The low energy behavior is basically K. So it behaves as K. So when I include this result, so it's proportional to K. When I include this into here, what I get is the absorption cross section behaves as 1 over k. 1 over k. You have 1 over k squared times k, and so you have 1 over k. So you can, with the simple model, just looking and with the notion that of the phase shift that we've seen before, we can easily see what's going on and understand this kind of strange behavior in the fission cross section. So the question is, what is the shape of this kind of potentials? Well, we work in nuclear physics, so everything has a Wood-Saxon shape. Or sometimes it's a square of a Wood-Saxon. The very general shape of the potential is the following: you have a real part, and you have two terms of the imaginary part. You have a Wood-Saxon and then a derivative of a Wood-Saxon, which is basically, you should imagine, so just to remind you, a Wood-Saxon has this very general shape, so with an inflection point at the radius of the Wood-Saxon, and the slope here, which is proportional to this diffuseness. You have a radius and you have a diffuseness. That's the expression of the shape, and it has basically that sort of a step function shape. So when you take the derivative, you derivate something, you had something which is surface peak. So that's at the surface of the nucleus, and you have a Coulomb part. The Coulomb is a little bit more complex or more realistic than the general divergent behavior of the Coulomb. It's usually an interaction between a point particle and a sphere of radius RC. So that's the expression that you get for this potential. And usually the radii are parameterized in this way. So you have a reduced radius, which is of the order of 1 Fermi, times a at the power 1/3, which is the mass number of the particle. Or if you have two colliding nuclei, you have the sum of the cubic root of the mass numbers of the nuclei A and B. So this you should pay attention when you look at the parameters of the potential given in the literature. Usually they are given in this way. So small radius, so it's a reduced radius, which is around 1.2 Fermi. The diffuseness is usually around 0.4, 0.7, up to 1 Fermi. Okay, and there are these parameters, so the depth of these terms and these radii are fitted to reproduce data. So you can get a very good. Yep. Yeah. Well, you fit that to the data. So you have, it can be a very complex process, because if you count here, you have 1, 2, 3, and then you have 9, and the Coulomb radius, you have 10 parameters, and you fit that to the data. So you have codes. Fresco does that. If you know Fresco, it's a reaction code. So it has a subroutine which is Fresco, that can fit the data to. So you give the data, you give the potential, and there is a search engine, and so within a few seconds you get a potential. Okay, so but with the time there were different ways to parameterize and to do the searches, because in the 1970s you had not very powerful computers, so you could not run a deep search over a large well, it's a 10-dimensional search on a very broad range, and so you needed to limit that. So depending on what kind of you will see different ways of fitting. So you take your data and you fit the parameters, and so there was a huge effort until the early 90s to do that. So to do systematic elastic scattering measurement and then infer optical potentials and from there to try to infer information about the nuclei. Yeah, yeah, yeah. The only constraint that you have is that W and WD have to be negative. That's what we've seen. Otherwise, you have a source term and it doesn't make sense. So if you let your search engine go very wild, then you get something that that could lead to something that has no meaning. The problem is there is no predictive power. You fit to the data. That's what you do. Okay. Then you can do that over different energies and the same system and try to get together something. So this is an example of Bonin and collaborators, 1985. So they did alpha scattering on nickel, zinc, nickel, tin, and lead. And so here is an example. That's once again the ratio to Rutherford. So you see these are these interference between Coulomb and nuclear power of the interaction, and you have this drop here. And so what they did is they did that at different energies. This is nickel with a kinetic energy of 340 MeV, and they did search with different, so they usually fit one parameter and then look for the others. And so they found, so you see for each of the energies, you have three different potential, and the three potentials are, the result of the three potentials are shown here. And so what you see is that you have these potentials are by no means unique. Depending on how you start your search, which parameter you fit, which parameter you fix, you get different answers. So that's just a way to remember that potentials are not observables. Yes. Excellent questions. So how you find the potential, usually you go in the literature, you start to search if you need one, okay, you go. In the 70s, there were compilations, so people took time to go through the literature and go for all. They stopped doing that, so you have to do that yourself, so that's a problem. You have global potential for some light nuclei, so for proton, neutron, deuterium, alpha, you have potentials that are so they did the search, and they did the search for each energy, and they tried to get a systematics in the change in the parameters. And so the first one who did that were Becketty and Green-Lees in 1969. By the way, this is one of the most cited papers in physical review of all time. I think it was at one point in the top 10 list of the most cited papers because everybody used it in nuclear reactions. More recently, you have Warner and collaborators, so that's the Chapel Hill potential, 1991. And even more recently, already even in this century, Koning de la Roche, they did a huge work to get the potential. For alpha particle, you have Nolte and collaborators in 1987. There is a website that shows all these kind of efforts, and you can also just plug the parameters that you want. So you have such target, such potential, and I get the result. So this is an effort led by MSU, the theory group at MSU, mostly Chloe Hepburn, doing this kind of work. But you need to know the range of validity, the target that you used, the energy, etc. And you need to look at the sensitivity of your calculation to these interactions. Now, to come back to the answer to your question, recently there is a huge effort to try to start from first principles. So you start from chiral nuclear interaction, and you try to derive the interaction. And so there is a very nice recent review paper by Chloe Hepburn, published in the Journal of Physics G, where different people using different kind of techniques came and show their work. So for nuclear target, the strongest effort is done for nuclear target, nuclear nucleus interaction. So Jimmy Roturo did some work in the past, Matteo Vorabbi using also chiral effective field theory, nuclear interaction, Andrea Idini from Lund. They did some significant work. These are 3 references. There are many more. You can go there and you will find them. For nucleus-nucleus interaction, that's much more complicated. There is a huge effort led by Sao Paulo doing this double folding technique. So here is one reference. In Japan, Furutomo did some work. Of course, for those of you who know him, Koa does a huge work on that. He's from Vietnam, and Victoria Durand started that when she was during her PhD in Darmstadt, and then we moved. So the problem is they are given in numerical form. So your reaction code needs to accept that as a numerical input. It's not a nice analytic form, and so you need to get to include that in your code. Here is the example of what Victoria did for. Here is alpha nucleus scattering. There is no fitting parameter here, so what you should look is the blue the blue range here. That's the sensitivity to the chiral effective field theory and interaction that you use, and through using dispersive relation to get the imaginary part of the potential. And so for different targets, so you have carbon 12, oxygen 16, calcium 40, and calcium 48 at different beam energies. And what you see is that there is a very nice agreement with the data. There is no fitting parameter. Okay, we see a disagreement here at larger angle, but that's where you start to be sensitive to the short range part of the nuclear interaction. And so there your EFT interactions start not to be accurate enough, because that's the short range. And the EFT, the idea is you start from, it's an N2LO interaction. So you start from the infinity and you go to shorter and shorter distances. If you want in your expansion, you stop here at the second or third, at the third term. So it's normal that the larger angle are not very well reproduced, but otherwise it's a very good agreement with the data. So this stops the part on the scattering theory. Here is a bibliography. So I had a question yesterday about what references. One of the best books is by Joachim. It's no longer published, but you can find on Amazon or eBay, I don't know, on eBay. But anyway, you can probably find secondhand books. There is a nice chapter, of course, if you do quantum mechanics in France or French-speaking part, you have to read Cohen Tanuji, and there is the chapter 10 of the volume 2 is a very good introduction to the scattering theory. More practical is the book by Carlos Bertolani and Pavel Danielevich, Introduction to Nuclear Reactions. It's more practical and it goes into more detail, heavy ion reactions. So something that Giuseppe will discuss this afternoon is also mentioned here. Ian Thompson and Filomena Nunes published a paper on nuclear reaction for astrophysics. So it is strongly biased to astrophysics, as the title says, but you have a very general view of scattering theory and reactions in general. And then if you like math and very clean, if you're a fan of Yoast functions and this kind of stuff, you have to read Taylor and his book on scattering theory, an excellent reference. So this will be on the website, so you can have a look at the list later. So let's start on the notion of halonuclei. If you have a little bit patience, it's yes, okay, yeah, 5 or 10 long minutes. So in the 1980s, no more math, so that should be more relaxing. It's excellent to start the discussion for the lunchtime. So in the 1980s, the first radioactive ion beam facilities started. So one of the first was Berkeley, and Isao Tanihata, so from Japan, did an experiment there. And one of the first things you want to know about the nucleus is the size of the nucleus. And one of the easiest cross-section that you can measure is, as what I have mentioned, is the interaction cross-section. So you take a beam of exotic nuclei, a nucleus, you send it on a target, something that you know, carbon, beryllium, something simple, and you look at what's coming out, and you count only the elements where you change your projectile has changed. And so that's how you measure the interaction cross section. It looks very simple. At the time, it was very difficult. The beam was not stable. Very rare nuclei, so the intensity was low. You had probably lots of crap in the beam, so you needed to do a proper analysis. But Tanihata is a good experimentalist. And so he published in 1985 his results. And here is a figure that shows, so you can do a sort of it's a high energy reaction. So you can have you see the cross section, the nuclei colliding as hard sphere. And when they touch something highly unelastic happens, lose some nuclei, so that counts for the interaction. And so it's basically the cross section is the surface of a disk, which has so you imagine two solid spheres coming in. When they are far away, they do not interact, so nothing happens. They can't exchange anything. But when they come close to each other, they touch each other, something highly inelastic happens, and the projectile will not come out as it came in, and so it counts for the interaction cross section. So that's the formula that they use. And assuming that you know the radius of the nucleus that you use as a target, you use carbon. If you do elastic scattering, you know the radius of carbon. So you know this one. That's what you want to extract, and that's what they did. And they did that for 4 different kind of beams. So a beam of helium, a beam of lithium, a beam of barium, and a beam of boron. And so you assume that the radius should be about 1.2 Fermi, A at the power 1/3. Okay, so that's what you expect. And this is the dotted line that you see here. And you see indeed that most of them, this is helium-4. Helium-4 is very compact. So of course it's smaller than the size that it would have in this behavior. But what you see is that most of the nuclei follow the shape. So most of these exotic nuclei have a typical behavior and are dense, compact nuclei. But some of them stick out. So one of them is here. It's lithium-11. One is beryllium-11 here, and beryllium-14. So they are larger than other nuclei. And so at the time, they had no idea what was going on. So one possibility is you have collective excitation. Okay, it's light nuclei. It's unlikely to have a collective excitation in the nucleus, but you could imagine something that is strongly prolate or strongly oblate, and that could explain this. But another possibility was because it happens when you just add one or two extra neutrons. And so maybe something happens to these neutrons. And so what they look at is also the 1 neutron and 2 neutron removal cross section. So they measured that. So just the channel where you remove 1 neutron or 2 neutrons from the nucleus, and they compare that to the difference between the interaction cross section of the nucleus and of the core. So the nucleus minus 1 neutron or minus 2 neutrons. So barium-11, you remove 1 neutron, barium-10 core. So you look at these two values, you do the difference of the interaction cross section, you obtain that value. And when you look at the 1 neutron removal cross section, you get something of the same order of magnitude. So it's the valence neutron that plays a role. So it's the valence neutron that has something weird. And so other experiments were performed. So I like this plot that much later, but it's by Sauvant and collaborators. They did an analysis where they remove the cross section and they look at the parent momentum of the core. So the nucleus arrives, the neutron is removed, and you look at the parent momentum of the core. And this gives you some information. And you see most of them have rather broad distribution, but some of them, so I'm sorry, they didn't measure beryllium, for example, or lithium in this case. But carbon-15, for example, has a very narrow distribution of the core. If you assume that the reaction is taking place at high energy, the neutron is removed, and the core has the momentum of the core after the reaction. It's adiabatic, if you want. So you assume that the reaction takes place quickly, and so the core retains its momentum, the momentum distribution that it had within the nucleus. Narrow momentum distribution, what does it mean for the expansion, the radial distribution? Narrow momentum distribution, what happens for the radial distribution? It should be broad, okay? And so it means that you think that the spatial core neutron distribution should be broad, and so you should have what we call the halo nucleus. So the name was coined by Björn Jönsson from Chalmers, but it explains very well what happens. So what happens is you have a compact core which has the same shape as a usual nucleus, but you have one or two neutrons which are loosely bound. So they are there is a small 1 neutron or 2 neutron separation energy, because thanks to that, you have the valence particle tunnel inside the classically forbidden region. So you have a sort of a diffuse halo composed of the valence neutrons around the compact core, like lithium-11. And so the expansion of the halo is very big. So for example, for lithium-11, it doesn't mean that lithium-11 has the same radius as lead-208, but the extension of the halo is basically as big as the size of lead-208. So it's a very strong and very, not magical, but purely quantum quantal structure. So here is the lower left corner of the Segre chart, nuclear chart. In black, you have the stable nuclei, you have the beta decaying nuclei here. In yellow, you have the 1 neutron halo nuclei, so beryllium-11 that was mentioned, carbon-15 I've mentioned just before, carbon-19 is also 1 neutron halo nucleus. Now you also have neon-31. And then you have also 2 neutron halo nuclei like helium-6. So helium-6 is seen as a helium-4 core plus 2 valence neutron. Yesterday, carbon-22 was discussed, so I should change the color of this one, and it is thought to have a 2 neutron halo halo structure. You also have proton halo nuclei are possible, so can have the same thing, but because you have this Coulomb barrier, the extension of the wave function is much less probable. And so, as was mentioned yesterday by David, 2 neutron halo nuclei are Borromean. And it means that the 3-body system is bound. So helium-6, for example, is bound. But helium-4 and a neutron isn't bound. There is no helium-5. So helium-5 should be here, and there is nothing there. It's just a resonance state. And there are the dineutron isn't bound as well. So there is no dineutron system. So why Borromean? The name was coined by Zhukov, and it comes from the Borromean rings. The Borromean rings are 3 rings entangled in such a way that the 3-ring system is bound, but if you break any of the 3 rings, the other 2 get loose. So if you look at that, you have the feeling that these 3 rings are really entangled, that there is something that they hold to each other. But if, for example, you remove the green one, you see that the blue and the red you would basically go away and not be bound. And so the name Borromean comes from the Borromeo family. It's a noble family from northern Italy, and so they had palaces on the Lake Major. So when you go there, it's on their coat of arms, actually. So that's why. And so when you go to these palaces, you see these 3 rings everywhere. So this is taken from a window from the palace on Isola Bella, on the Lago Major, looking at Isola Superiore dei Pescatori. And so you see these rings everywhere on the flower pots, on the doors, and on the windows. And so here is the picture of the lake taken from Mottarone, which is a hill of a mountain So here is the Isabella, here is the palace, and the view was taken, the picture was taken looking to this island. So it's a very nice place, and you can visit. And so I will stop here, and we will see how we can study these halonuclei tomorrow. I will probably start with a short introduction before going to the exercise system. And what we will look at is this reaction tomorrow using the code that I have sent you. So you can work in groups. You don't all have to have the code working on your computer. You can also work with someone else and run the code together, and then work together if it simplifies the problem. So now it's time for lunch. I thank you for your attention. Enjoy the lunch and the afternoon session.